let us like start basically. So I will just what actually I will do, because it's an online mode. So sometime in online mode I should not like kind of like maybe lost somewhere because it's not like the one to one interaction. So maybe in the chat box someone can write if there is any issue of like audio or video problem, so I can check that also. Or maybe someone can maybe send me WhatsApp also from Professor Rahul's group maybe.
Yes,
So
yes, sir. We
yeah,
will
if,
do.
yeah, if there
If
is
there will
any
be
issue
no,
with that. Yeah, because
yes,
sometimes what happens, I experience like sometimes you get lost in between, and I was like going on, and then maybe there is some connectivity issue.
yes, yes.
Anyway,
This is yes.
yeah, so let us start with that, basically the basic Drude model. So so if I just let me just turn on the uh, kind of like the pointer here, or maybe the, yeah, or the laser pen. Let me just check the pen or pointer, whatever is there. Yeah. So you see, let us start with the Drude model. So this is like one of the very old model, which is now which is basically for the metals we talk about, where we consider in this model we consider metal like it consists of a positive charges which are immobile, and which is in which like there are electrons which are valence electron which are wandering freely in the metal. So that is a simple model. You have a sea of electrons which are actually embedded inside the positive ion cores, and they which is immobile. So mobility only for the electrons which are mobile, and they are free also. The another thing with this model is like it neglect electron interaction. So like this electrons are charged, we know those are the charged body, but the model actually does not in like account for the this interaction of the electron. It also neglect basically electron core interaction, which is like positive core, which we are talking about, positive ion cores in the lattice position. So that is also neglected in this model. So what I say, the Drude model actually completely neglects basically the Coulombic interactions, which is among the electrons or electron and core. The only thing which actually is implied inside the Drude model, that when the electrons are moving inside the crystal lattice, then they see these cores, and because of the presence of these positive ion cores, they undergo scattering. Scattering means the electrons are moving and they deflect. Actually they deflect because of that interaction, and that deflect in this deflection in such a way that they lose the memory, like they don't know, like it's like kind of they move into the random direction. So randomization is because due to the scattering events. So now I'm just showing you here. So you can see here basically these are the positive ion cores. So I'm just showing you, this is the copper ions. And these copper ions, because at room temperature, we are just talking about room temperature. Suppose in the room temperature these ions are having some energy, which is, I say, the thermal energy, which will be proportional to some so to the temperature only. So this thermal energy, because of thermal energy, these positive ion cores are vibrating. So you can see these basically these arrows just show basically their vibrations. And then here you see we are also showing one electron here, how the electrons are moving. So electrons are moving with some mean velocity u, and whenever they see some whenever they come into near to that positive ion cores, they get deflected. So they see this is, they are coming like in this direction, they get deflected, they get another deflection, and this is actually in the random directions. Okay, so these deflections are in the random directions. So so that is the idea basically about the Drude model. You have positive ion cores, electrons are moving, and they are moving with some mean velocity, and when they encounter the positive ion cores, they get deflected. So so that is the idea, and this ions are also vibrating because of the thermal energy. Now you see another thing which we need to understand here, that what are the other assumptions which are made in the Drude model. So one assumption is basically that between the collisions, so if I just say between the collisions, like, or between the two scattering events, like between, like, suppose it started from here, and this is one event, then this is a second event. So between any scattering events, the path is, you see, the path is, you see, is like the straight line. So path is straight line, moving, it is moving in the straight line, that's the idea. So it is moving in the straight line. When I say it is moving in the straight line, means any kind of interaction is ignored. Straight line means it's like, it's moving, it's not deflecting. So any kind of interaction, either electron electron, so this electron electron interaction is already ignored, that we understand, because of the electrons are moving in straight line. So which is reasonably valid also, because that's okay. But the effect of electron ion is also ignored. So we are not considering the potential of positive ion core, and that is actually completely invalid kind of assumption, but it was taken in this model. So other thing is basically that the average mean free time between any collision. So so the Drude model also talks about basically the mean free time, average mean free time, or the relaxation time. So what is that actually? So relaxation time means between any two collision, between any collisions, two collisions, like this is, suppose this is one and this is a second collision. Between any two collision, what is the time here? Suppose this time is tau, so that time is known as, basically, if you take, and then you take the average over basically all the charged particles, then basically this will give you, this gives us basically the mean free time. So this is the so the mean free time is basically the time which the in which basically electrons is moving without any scattering between two scatterings. So that is there. And this, another, the assumption regarding this mean free time in the root model is that relaxation time or the mean free time is independent of position and velocity of the electron. So that is another assumption, means it does not, it like, it does not matter whether how close is the electron with the positive ion core. The tau, actually, this mean free time, this or the time in this path, which is a flat path between two scattering events, always remains basically same. So that is the assumption. That is not actually, in reality it is not true, but we, that was the assumption here. So the fourth assumption is that the electron achieve thermal equilibrium by collisions with the lattice. So means electrons, after the collision, they uh, they come out in the random direction, and the speed, they also change their speed. So means after each collision, they, suppose they collide here, they collide, that means there's a scattering event here, and then electron like moves in the another direction. So basically after each scattering event, so both, like, the its direction of the is like mean velocity is changing, also basically its magnitude can also change, and that depend on basically the temperature of that particular region where the collision happened. So that is another another important point about the Drude model, that basically the electrons which are coming out after the event, after the collision, so their speed depends on the temperature of that local region. So hotter the region means more more the temperature of the region, or more vigorously this lattice ions are vibrating, the larger will be basically the, or higher will be the speed of the emerging electrons. So that is so these are the some basic assumptions about the Drude model, or some important think like thought about the Drude model, which was taken. And you see, one of the another thing is that electron here, unlike gas molecules, they are charged bodies, do you know that? And they are also moving under the in the background of other charge entities. So and these densities are also very large, around like 10 raised to power 10 raised to power 28 per centimeter cube. But still having like these facts, like they are charged bodies and they are moving, and the electrons are also moving, the electrons are charged, they are moving under the background of other charged bodies, and their densities are so large, 10 raised to power 28 per centimeter cube. But still Drude applied the kinetic theory, which is basically the kinetic theory of gases, which is for the metals also. And so, but there are some like the positive outcome also. But so this was very like surprising, but it gives us a good result. So so the application, let us discuss about the application of this Drude model. And what we will describe, will find out basically the electrical conductivity, DC electrical conductivity of metal. Out of like which, applying these models, how can we figure out the DC electrical conductivity? So if you see here, suppose this is my conductor of which is having a cross sectional area A. And suppose if I say, if n is the number of charge, number of electrons per unit volume, then basically if I would like to know, if I have a small section of this conductor which is length is d, then how much charge is there, we can figure out. So we just figure out basically the volume, because n is the number of charge per unit volume. So the total charge which is enclosed within this conductor, this section of the conductor, will be simply Ne time the volume, which is A time d. So now you see, now suppose we apply electric field here. Suppose the electric field we apply, so means this is my positive side, this is a negative side. We apply some voltage. So because of that, in the conductors, because of that, there is some electric field which gets set up in the x direction. So this is the x direction. And suppose this electric field is in the x direction, which is Ex, I'm saying. And what will happen now, the electrons are there, electrons are everywhere in this metal. So immediately these electrons, because of this the electric field, they will feel some kind of force. So that force will be, each electron will feel some force. And that force, because of electric field, will be simply E time Ex, which is the basically the field in the direction, in this direction. This will be the force, charge time the electric field. This will be the force which is basically felt by all the electrons immediately. And because of that, these electrons will acquire some net velocity. They will acquire some net velocity in the x direction. So they will acquire the velocity in the x direction, since they are electron which is negatively charged. So this is negatively charged. So the force and the electric field, the force and the electric field, they will be in the opposite direction. So electron, that's why you see the arrows are in the opposite direction. The electrons will move in the opposite direction. So now what we'll talk about basically, so we'll figure out basically how much is the, what is the value of this current, which is known as the drift current, which is produced because of the application of the external electric field. That we would like to know. So what happens, so there will be, all electrons will acquire some kind of velocity in the x direction. And if we average out all the electrons, their velocities in the x direction, and that is known as the drift velocity. Okay, so that is the drift velocity, which is basically the instantaneous velocity in x direction, and which is averaged over many electrons. So something like 10 raised to power 28 electrons per meter cube. So this is a very huge number, you have to average out. So now we can just figure out basically, just like how much is the current, actually how much is the current density in the x direction. So current density is simply current divided by area. So this area is, this is the area, so of the conductor. We just say this is, suppose A is the area, I is the current which is moving. Current I can write down in terms of charge, delta q by delta t, how much charge with that is moving, or how much charge which is crossing the area A in time delta t. Now the total charge we have already calculated before, but now also we can figure out. So the total charge will be simply E time n A and v dx t, where v is the drift velocity. So if you just a little bit you just see a little bit, it's not like it's easy to figure out finally that our current density in x direction will be NeV dx. Okay, so this is my current density uh, uh, in in the x direction when you apply basically the field in the x direction, Ex. Because of the field, there will be a drift velocity, and because of that, there will be a current density. So that we could able to figure out. Now, so we just figure out that. Now we'll try to find out the another important a relation, that is basically the relation between the electric field and the current density. So how we figure out? So you see, let us determine basically the velocity uh, when we apply the DC electric field to the matter. So suppose we just consider a single electron, and whose velocity immediately after the collision at time t equal to 0 is suppose v0. Like we can just go here and see, suppose we just take this electron, and before the collision, just after the collision, its velocity is suppose here v naught at time t. Okay, at time t equal to 0, its velocity is suppose v naught. Okay, now let the electric field is E, and its velocity at any given time t will be, simply you can see, I can just apply the because in between, I can just assume that in between uh, the path, it is the linear path, there is no other interaction. So I can use basically this equation, which is simply we can apply the Newton's equation of motion here, that the velocity v is u, like v is u plus at, where a is the acceleration. So a acceleration is simply, you see, is force divided by the mass of the electron, and force is simply minus E time E electric field divided by m. So if I just put there, so we get this relation Vt, which is time dependent, V naught minus E by T. Now, so here we assume that electron does not suffer any collision in between. Between two successive collision, the electron path is straight actually. So, or it is basically there is no other interaction. So now if I take basically, so this is for a single electron. Now if I just average this velocity, this which is the drift velocity for all electrons, means if I take all electrons, if I average for 10 raised to power 28 per meter cube, like this much number, if I average that out, then you know that if I average that out, this, because you see the electrons after the collision, we that is the assumption of the Drude model, that they basically randomize, means their directions changes, they randomize, so there is no net direction in which they are moving. So what we can say, that if I just do the time average, if I do basically, if I average for all the electrons at a given time here, sorry, if I, like you take the time average of this equation, if I take uh, the average, sorry, let me write down average over a minute, not wait a second, something. Yeah, I think, yeah, I think there was some issue. Mhm. Wait a second. Yeah, let me share it again. Yeah, it got like my slide is not moving. Let me just try that again. I'll just maybe, yeah, so I think it will come out. I'll just upload that. Let me open it again. So still, can you see my slide or no?
No, sir, it's not visible.
Okay, let me just try again. Can you see now?
No, sir. Yes, yes, sir. It's visible now.
Yes, Dr. Saab, it's visible now.
Okay, okay, let me just yeah. Yes, some time. Okay, so yeah, I was telling about, like, if this is the equation which we got basically, which is because of Newton's equation of motion for the electron. So if I take the time average, if I take basically the time average, no, 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 sorry, if I take the average over all the electrons, average over electrons, which is here, which is basically, if I take the average of this velocity over all electrons, and these numbers are very high, huge. There's something like 10 raised to power 28 per meter cube. If I take that, you see, then what will happen? This basically V naught term, which is basically just immediately after the collision over the all electrons, will be zero, because you see, the after I just told you, after the collision, the this randomize. Okay, there's no net, no fixed direction in which electrons are moving. So this will be zero. Then we'll get basically the average drift velocity. If I figure out, that will come out to be simply, if I just say E time E, and this T will be tau, which is the collision time divided by the mass of the electron. So this is my drift velocity. So now we have already deduced before that my J, if I apply the electric field, my J, which is Jx, that is basically the current density, is simply Ne time Vdx or Vdx. Yeah, this we obtain, and we just got that basically our J. Yeah, this is Vdx. I can write down. So if I just equate both, I just input the value of drift velocity here, I get J, which is current density, as a function of the electric field. So you see what we learned, the current density is actually in the direction of the electric field. So you apply the electric field, they are proportional. And because you see, m mass of electron is constant, n E is constant, and n is basically the number of electrons per unit volume for a given material. It is constant. Tau, which is the collision time, that is also a parameter of the specific to the metal. So this whole, which is inside the bracket, is the property of the material. So I can also write down, you can write down this like sigma E, where sigma is known as the conductivity. So this is basically nothing but your Ohm's law. This is a microscopic of Ohm's law, which relates the current density to the applied electric field sigma, where sigma is the material property. Now, different metals, they have the difference in the n, which is the number density, or they have different collision time, or sorry, mean free time or relaxation time. So that actually cause the difference in the conductivity among different metals. So this model, and the resistivity will be 1 over divided by the conductivity. So this model is very, like, if I just input, like people like they input the values, if I input the value of charge, will input the value of mass, or this tau, which is mean free time, and n, then we can find out what is the conductivity. So these values are like in very well agreement with the experimental obtained value for the metal. That was the success of the Drude model. It's a very simple model, and we can figure out how this model correlate the microscopic properties, which is the collision time, with basically the macroscopic property, that is the conductivity here. And that is a kind of a success of that. So so now you see, we just learned that sigma is your n time e squared tau by m, and we learned that your J is n time EVD, and we also learned this is going to be sigma time E also, where E is the electric field, and I can just write down in that direction. So if it is X, I can write down X, here also X. So if I correlate, if I just use this basically these two functional form of current density, then we can get this relation, that drift velocity is proportional to your applied electric field, where tau is the collision time. Now basically you see, there is another quantity which is very important, and that is basically your mobility. So how we define the mobility? Mobility is simply, basically, I can define the mobility, that is simply your drift velocity if you divide by the electric field in that direction. That is going to give us the mobility. So mobility comes out to be E tau by me, which is also a very important number. So the mobility, what the mobility tells us about that? So it tells us basically how fast electrons is drifting. When you apply the electric field, how fast they are drifting. So if the electrons is not highly scattered, means if I have the metal in which the scattering events are less, or they are not highly scattered, in those cases the relaxation time will be large, and that will also make the mobility large. Means means less scattering, more higher the relaxation time, and the mobility will also be larger. But we have to keep in mind that the large mobility does not always imply high conductivity. Why? Because if you see, the conductivity and mobility relation are like this. So means it also depends on the concentration. Like, so if maybe the material might have the larger mobility, but it can have a smaller conductivity. So now this is something like, which is the success of the Drude model. We can just get some very interesting parameters, like the mobility can be determined, the drift velocity and the conductivity, those can be determined, and to a very good extent these values are also very reasonable, which were found experimentally also. So but there is one very interesting thing here which we have to notice here, and that is basically that, see, if I just talk about, if you see, one can think of, okay, let us we can think of like, okay, this is like same thing, like we can apply the kinetic theory of gases for ideal gas, kinetic theory of ideal gas, where we know we can just also determine the mean velocity or the mean speed of the ideal gas atom. But in this case, you see, this model does not like resembles to the kinetic theory of gases. Actually, I cannot take that. The reason is because here you see we have not like assumed, but there is still some electrostatic interactions. We are dealing with the charged bodies. Conduction electrons are charged bodies, and the positive metal ions are also charged bodies. So there has to be some kind of potential energy also involved there. So there is kinetic energy also and potential energy also. So now we can get the difference here. So one can see here, if I just talk about the average kinetic energy of an ideal gas atom, that will be simply 3 by 2 kT. You can get from the because there are 3 degrees of freedom, so each degree of freedom will have half kT. I can say the 3 will be 3 by 2 kT. So each ideal gas atom will be having 3 by 2 kT atom. So if there are n number of that, so you'll get 3 by 2 nkt. So that will be your average kinetic energy for the gas, for like per unit volume, you can say that, or energy density. So if I just talk about the conduction electrons in metal, and that is not the same thing. Like I cannot say that the conduction electrons is also having this kind of energy 3 by 2 kT. Why? Because the electrons are fermions. So they are fermions, they obey Pauli exclusion principle is there, and that will basically hinder all the electrons occupying the same low energy state. So means even we don't want, but electrons, since they are fermions, so there will be a distribution of the energy, and the electrons will start filling up the energy levels, and depending on the number, because that is very high, the electrons can fill up to the maximum level, and you know that level is Fermi energy. Okay, we will discuss more maybe in next class. But that Fermi energy, and the value of the Fermi energy, if I talk about this Fermi energy, is basically several electron volt. This is several electron volt, which is the typical order of metal. Like if I take, like if you take gold, it is around like 5 electron volt. Whereas you see, if I just talk about the room temperature energy kT, if I just say for room temperature, it is something like 26 milli electron volt at room temperature. I'm saying this value of kT, so which is around like 300 Kelvin. So means if I you see, that's why the mean speed of ideal gas atom will be around something value, typical value is around like 500 meter per second, whereas the mean speed of conduction electrons will be around 10 raised to power 6 meter per second, which is 1/100th of speed of light. So actually, so electrons in the basically electrons in the metal are moving really very fast. Actually, they are moving with the speed of 10 raised to power 6 meter per second, and that is not because of the thermal energy, because of the Pauli exclusion principle, because their Fermi energy is like is tens of electron volts, several electron volts, is much higher than the room temperature energy. So they got that kind of thing because of the quantum phenomena. So that basically just so which is a difference here, which I thought I just share with you. Now you see, let us do one problem here. So if I you see, so if here we need to, this is one example, here we need to do determine basically the mobility and the relaxation time of a conduction electron in copper at room temperature, and the conductivity of copper is given, and uh, like the number density of electrons are also given, n is given, and this number is your sigma conductivity. And we need to figure out the mobility. So see, you can just use this formula, simple. So here we are, I'm not going to do that, it's already done, you can just try. So we just figure out basically conductivity divided by En, and we got the number here. This is the mobility. Now same way, I can just figure out basically the collision time also. These are all numbers are actually the real numbers. So if I just figure out basically the mean free time or the relaxation time, that comes out to be 10 raised to power minus 14 second. So which is also fine. Now what actually next is, what is the next thing is, like what is the mean free path? Mean free path, that is basically like how much time the electron is actually moving without between two successive collisions. So that we see, I just in multiply by the speed which is given here, mean speed of electron times basically the collision time, the mean free time. So that comes out to be 39 nanometer, which is also reasonable number. So these are numbers, like you can get some idea. But the next thing which I'm just going to discuss with you little bit, we have to be a little careful here. So next question is, what is the applied electric field that will impose a drift velocity equals to 0.1% of the mean speed? So suppose if I assume my drift velocity, see the drift velocity is always much smaller than the mean speed. So electrons are moving with 10 raised to power 6 meter per second. That is without any electric field also they are moving, because they are fermions. So if I assume that my drift velocity is 0.1% of basically the that mean velocity because of the because electrons are fermions, or the electrons which are moving without applying the electric field. So if I'm only assuming they are 0.1%, so that means 0.001 of u, and that comes out to be 10 raised to power 3 meter per second. So this is my now the speed. Now what will be the electric field? You know that I can figure out the electric field by this relation. If I know the mu d, which is drift velocity, I can easily figure out, and it comes out to be 10 raised to power 5 volt per meter. So if I use this is a very huge number, this is a very high field. If I use this thing and figure out basically the current density, I can figure out the current density, which because sigma I know, so it comes out to be around 10 raised to power 13 ampere per meter square. So here I'm saying the copper wire is having a diameter of 1 mm. So you have a copper wire, and this diameter is only 1 mm. So it means in this 1 mm, if I take the area here 1 mm, so the current which I will be of the order of 10 to power 7 ampere. It means that if you apply basically, it means this current for this problem which is moving in this wire of one diameter is 10 raised to power 7 10, so 10 raised to power 7 ampere, which is very very high. So see why it is coming this much. So it means this number which we assume, like which is 0.1 kind of percent of mean speed, is not true. It means the drift velocity is still much smaller than that. And actually in reality, if you see, the drift velocity is much smaller than the mean speed of the electron, and it is typically of the order of millimeter per second. Okay, so that is the order. So so the drift velocity, it means when we apply the electric field to the conductor, for all practical purpose, the mean speed is unaffected. Means the speed you apply the field or you don't apply the field, the electrons are moving with the 10 raised to power 6 meter per second. So this speed is getting unaffected when you even you apply the electric field, because the drift is only millimeter per second. So we have to understand basically the difference between the drift velocity and the mean velocity. Now some of the, you see, so some of the like the outcome of the Drude model we have already discussed. It explains well about the conductivity, mobility, and also the current density. uh, but there were one very some problems with the Drude model. Before that, it conductivity actually depends on the temperature. But you see, what we determine the formula for the conductivity is Ne square tau by m, where tau is the mean free time. So there is no temperature term here. So conductivity in reality, in experimentally, it is found that it depends on temperature, but it does not come out from the Drude model. Also, the if there is an impurity or the crystalline nature of the material, it does not actually encounter that. So those are the problem. And also in some material, the larger mean free path will observe at low temperature of the order of centimeter, which it cannot account. Also the small contribution of specific heat, also this is the major drawback actually, the specific heat. So you see, if I just talk about the electronic specific heat, it is du by dt at constant volume. If I say is a this is at constant volume, so du by dt. So the Drude model, you see, according to the Drude model, the electrons, you see, if I just apply the classical equipartition of the energy, so there will be total energy u will be simply must be 3 by 2 time kt kBt. Okay, so if I take basically du by dt, then it comes out to be simply 3 by 2 nk, because this is for one atom. And then if I just assume one electron, if I assume basically n number of electrons, then the electronic heat capacity should be 3 by 2 nkb, and which means it is independent of, which is also independent of temperature. But what was actually experimentally found was very strange. Then experimentally, when you do the experiment at especially at the low temperature, the heat capacity of the metal follows this relation. Means heat capacity is gamma time T plus AT cube, and which means that the even at like high temperature, it is proportional. This ATQ term is more pronounced in the low temperature part, which is because of the phonon component, which we will not discuss. But the this gamma T term, which is basically that your heat capacity is proportional to temperature, which is but the Drude model says that it is independent of temperature. Also the value which was found, uh, at room temperature, the electronic component of heat capacity of the metal is, which is found by experimentally, is much smaller than the Drude prediction. So this was a severe falling of this model, uh, and which says that we need to go for. So the next model was basically Sommerfeld model, but maybe uh, we will discuss maybe later about that, maybe if time permits. um, some portion we'll discuss tomorrow. So now we'll discuss about another very interesting fact here, that is the Matheson's rule, and that actually talk about basically just take care of the, because resistivity, you see, has two parts. It is basically the ions are vibrating, which you can see here. I'm just showing you. These are the all positive ion cores which are vibrating in different directions, random directions, because of thermal energy. And the electron, this is electron, which is moving charge particle, they get actually scattered because of this lattice, and we get basically, because, and this is the mean free time, because in next collision occurs here. So this tau is basically the collision mean free time. So what I'm saying, if I just assume that there are some impurity also, means like if my, maybe if I say my metal is having some impurity, which is shown by the dark circle here, big dark circle. Because of the impurity, what will happen, the impurity atom might have the different size compared to your suppose if this is copper and you get some impurity, maybe some other impurity, maybe some zinc, which is different size, so, or iron. So because of that, there will be a lattice will get distorted nearby. So nearby lattice will get distortion, and because of that distortion, basically this you see, we have two events. One, which is I'm just talking about the scattering, or because of the lattice, or the another scattering will be because of this, at this position, because of impurity. So in given metal alloy where we have basically the impurity atom, you can see we have two types of collision event. One collision with the impurity atom, other with the lattice atom. So one can write down the mean free time, which is tau, total mean free time, as basically like you have 1 over tau t, which is the contribution because of the lattice, and this is the contribution because of the impurity atom. So you see, the smaller, which one is the smaller actually will win actually, because that you know that. And then I can, based on that, I can write down the resistivity, because now because of the difference in the mean free time, we have two events, so we will be having basically our resistivity will be having two parts. One is the lattice and other will be the impurity. So I can write down like the total resistivity is lattice part plus the impurity. And you see, the impurity part is basically not temperature independent. That is the thing, because as impurity is there, it's not like having any kind of like this, like big impurity I'm talking about, they don't have the correlation, impurities are far away. So this impurity part is temperature independent, whereas this part is temperature dependent. So you see, I can just, this is the same thing. So in general, I can write down the net resistivity will be having two parts. One is temperature dependent, this is because of the lattice, and temperature independent, which is basically because of the residual resistivity, or which is because of the electrons which are scattering by impurities, dislocation, interstitials, all kind of defects, vacancies, grain boundaries. So I can write down that. So this is there. So this gives us the idea basically how if you have the alloy, if you have the impurity, how the resistivity depends on the impurity. We can talk about that. Now you see, the resistivity also depends on the temperature, and one can write down the temperature coefficient of resistivity, which is defined as the fractional change in resistivity per unit temperature, like this in this function. Or we can write down, this is very much similar to basically your thermal expansion also. Like you have a material, you put under the you change the temperature from T to T naught to T, then basically this is delta T, and because of that your length gets changed. The same way basically resistivity also get changed from its initial value. So this is a very pretty kind of like a linear relation. which is assumed there, and we can but in this case alpha naught is your coefficient of resistivity. So here you see this is the typical curve. Actually, you can see the resistivity, how resistivity depends on the temperature. For large temperature, like high temperature, more than like 200-300 Kelvin, more than room temperature, actually it is pretty resistivity is its experimental curve is proportional to the temperature. It's, for most of the metal it is like that. But if you go for the low temperature, for the low temperature part, then the resistivity, because the phonon parts also comes into account, then the resistivity have different correlation. It can be like some number n, which varies differently. So here t to power 5 dependence, it can be t to power 3. So there can be a different dependence are there. So it is not like for, it depends on that what kind of material we are talking about. So the resistivity becomes strong temperature dependent as we reduce the temperature. You see, as you go to reduce under 100 Kelvin, it is a very strong function, and then resistivity never goes to zero if you mean increase reduce the temperature, because the impurity will always be there. The residual resistivity will always be there. Now in general how the this is the rule which says it's a rule which talk about basically how, if you know the resistivity, how it depends on the temperature. So if you have T naught is one temperature at which the resistivity is rho naught, and you need to figure out at any other temperature. So it's a general rule how the resistivity depends on temperature, where you see n is a number here, n is a number. So like you can see in this example, if I say suppose we have a bulb here, 40-watt bulb, which is working at 120 volt, okay, and this has a tungsten filament. This is my tungsten filament, and which is the length of filament is given and diameter is given, its resistivity is given here, and we say that it is varying with T1 1.2. It means my n is 1.2 here, and then we need to figure out the temperature of the bulb when it is operated at rated voltage. Rated voltage means it is operating at 120 volt. So now you know that bulb is dissipating 40 watt at 120 volt. I can easily figure out the current, which is power divided by volt. 40 watt divided by 120, it comes out to be 0.333 ampere. It means this is the current which is flowing in the tungsten. Now the resistance I know, the resistance is simply V by I know the current. Now I input here, the voltage is 120. That will give me the resistance of, this will be the resistance of for basically the tungsten filament. Okay, now this is a simple relation. So I can figure out from the resistivity, which is R is rho L by A. I can figure out basically the resistivity as a function of temperature with that, which comes out to be like this. Now I know basically rho t is simply, you see, rho t is simply rho naught T by T naught and 1.2. I'll put 1.2. So you just input the value and you can figure out basically the temperature of the, so this will be the temperature T, which is basically temperature of the tungsten element. So this is the so this is the general equation, the general where n varies with the, depends on the basically different types of the material also. Now let me just maybe just because of time, let me just or maybe I can just continue with that. Let me uh, discuss another rule, which is the resistivity for solid solution, which is Northern rule. So we have discussed basically the Matheson rule, which tells us how the resistivity depends on the temperature, like this, how the resistivity depends on the temperature, this law. There's another rule which is known as Northern rule. So what that actually talk about, suppose we have a binary alloy, means we have two metals, like if in this case suppose we have copper and nickel. So I made a binary alloy of copper and nickel. The only thing is that these two metals has to be of single phase, number one, and also they should have the same vacancy with same valency. So they means they should be in the same column in the periodic table. So if I have that, so for that, what is there actually, I can just see, if I mix, if I change, suppose this is 100% copper and I have some resistivity value, and another end we have the resistivity of nickel, this is copper. Now if I start like making putting nickel inside the copper, means like suppose at this, at when we have 20% of nickel and 80% of copper, resistivity increases. So as you keep on basically putting the like including the impurity in terms of basically, or making the alloy here, not saying the impurity, alloying maybe, then depending on the atomic weight fraction, as on not the weight fraction, atomic fraction of the solute atoms in the solid solution, then basically the resistivity increases. So this is a semi-empirical rule, means how the resistivity depends on the atomic fraction of the solute atoms in the solid solution. So see, this is semi-empirical rule, means this is not determined purely from the theory, but it comes from the experimental observation also, experimental results also, where C is the constant. So if I know, so this part will be basically the resistivity because of the impurity, because you input the impurity, and that impurity means now the nickel will be impurity. If I have solution where we have 20% nickel, 80% copper, so 20% nickel will be the impurity here. I started with 100% copper, suppose. So it means if I know the atomic friction, I can determine the resistivity because of this inclusion. So what is the total resistivity of the material alloy? Total resistivity will be simply the matrix. It means the copper, the resistivity of copper plus the resistivity of basically your this, because of this alloy we made the binary alloy. And so we can just, it is very clear if I just we do this simple basically one example here. So suppose we take the 98% of gold and you include 10% of copper. This, see, this is very much used in the electrical contact, DC electrical contact, because gold has a very good conductivity, but the problem is gold is mechanically soft. So if I put the copper inside that, it provides the hardness of the material without sacrificing the corrosion resistance. And you see, if I use this gold, which is my the matrix, which is the matrix, the host material is gold, and only we include the 10% weight percent of copper, and C is the Nordheim coefficient. So suppose we would like to know what will be the resistivity of my 90%, 98% of gold, where we have 10 weight percent of copper. I know the resistivity of gold. So how to determine? So first of all, we need to convert this 10 weight percent of copper into the atomic fraction. So atomic fraction, you just use this formula. I think most of you know that, how to use that weight percent into the atomic fraction. If you get that, we get the basically atomic fraction like 0.256. So if I input this value here, and you know the value, you see we get the value of this alloy. So this is the alloy, binary alloy. We get, this is the resistivity for the binary alloy of 90% gold and 10% of copper here. Now maybe I'll continue maybe in the next lecture this AC conductivity part. So I'll just stop here, and let me know if you have any query till now. Then maybe we'll take 5 minutes maybe rest, then we can continue.
Yes, sir. Thank you. Thank you very much, sir, for a very wonderful lecture. Ankita, I am audible?
Yes, sir, you are audible.
Okay, very good. So, sir, participants have written few questions in the chat window.
Let me just read that.
I think there are 1 or 2 questions. One question they have written at Yogesh Kumar. Sir, what will be the impact on mobility if we use semiconductor over the ferroelectric material?
Okay, so the mobility of semiconductor, if you have the semiconductor material, the see, in that case, I just, you see in Drude model, when we apply the Drude model, the mobility depends on the scattering centers. So if you have very large number of scattering centers, like which is the case in case of metal, you have, because in case of metal you have very large number of electrons, so there are and they are moving with that within the lattice. So the mobility is normally is like smaller in case of basically mobility in case of metals is relatively smaller, but there basically the scattering events are less in semiconductor. In general, the semiconductor mobilities are larger, but it is not like always true, because you see mobility depends on the number it depends on n also, which is the number concentration of electrons or concentration charge particle also. So depends on the so it depends on the material to material, it varies from material to material, but one can figure out, so from the material, you know, the formula, you can determine basically.
Yes, yes, sir. So it seems there is no more question. So there is a question is by Prahlada Rao. What is fermion? They want to ask about the fermion.
Okay, so maybe like because tomorrow we are going to discuss about the density of state Fermi Dirac function. So I will basically maybe I'll take care of that. But fermions
Yes.
are like, see, electrons are fermions, and there are three types of statistics. One is Maxwell Boltzmann, Fermi Dirac, and Bose-Einstein. So depends on basically the spin. It depends on the spin of the electron. So half spin electrons are known as fermions, which follow the Fermi-Dirac statistics. The particles which follow the Fermi-Dirac statistics, where the wave function is antisymmetric. So the antisymmetric wave functions, they are known as fermions, and basically the integer number, the spin particles are known as bosons. So like if say the photons are bosons, electrons are fermions. So we have similarly we also have like other particles also which are fermions, like protons are also fermions, so which has spin half. Yeah.
Yes. Yeah. Thank you, Professor Singh. So now, if there is no further question, we can take a break of 5 minutes,
Yeah,
and
okay.
next lecture we can start around 4:07 or 4:08. Okay, it's 2 minutes after 4, so we can start. Let's say 7 minutes after 4.
Yeah, sure. Okay, okay, fine. Okay.
Thank you, sir. Thank you.
So, Sir Rahul, can I start maybe?
Yes, sir. Yes, sir. You can start.
Okay. Okay. So my slides are visible.
Yes, visible. It's visible.
Okay. Okay. Fine. Okay. So like we have just discussed about basically the Drude model. Then we figure out the conductivity, some parameters we discussed. Now, you see, now I'm just talking about basically when we apply the DC electric field. Okay, that we apply the DC means it's not depend on time, it's a fixed electric field we apply, and then because of that the electron will get drifted out, and we call that drift velocity will be actually in the, basically it will be along the direction of the field. Now the drift velocity in general can be time dependent also, means like we have not discussed about any time dependency of the drift velocity, but they can be time dependent. That can be time dependent due to the fact that, like the field which we are applying, so field we are applying, suppose this field can be, if field is time dependent, number one, then my velocity can be time dependent, or the we just turn on the field. Okay, means like you just turn on, switch on the field. Okay, so that is basically, or the electron just started accelerating. So there are two conditions by, because of that the drift velocity can be time independent. Now you see that now we'll try to basically get some formulation when we have the time dependent electric field. So because before that, in general, we'll discuss basically one case. Suppose uh, I can just talk about basically that conduction electrons are moving in solid, and we can think of my solid as some kind of a viscous medium. So this scattering event, because of that scattering event, is like maybe it's like the my medium is slowing down this velocity, drift velocity, and because of the scattering events, because scatterings are there, then my velocity is not going to be built up to infinity. You see what I mean to say is, electron is moving, so the force on the electron will be simply minus E time the electric field. Now you see, if I can write down the force as mass time acceleration, and I say, so this is mass time acceleration, you see. So what does it mean? I can just also write down, it is like dv by dt will be minus E by me. Okay, so it means that basically if my you see, it is directly proportional to electric field. So means over the time, so v over the time the velocity is going to be built up, because this E is fixed, m is fixed, and small is charged. So v is proportional to t. It means if there are no scattering events, my velocity is going to be built up to infinity. So what the purpose of the scattering centers are there? They actually try to pose some maximum limit here. So I can assume this solid as a viscous medium, um, and so I can write down basically some kind of equation here. The equation of motion will be, this is my force which is applied on the electron, E time E, and then we will have a basically resistive force. So my driving force is due to the electric field, and there will be a resistive force that is because of the scattering centers. I can just say that resistive force is proportional to the drift velocity. Normally the drag, you also remember the drag forces which are proportional to the velocity itself. So I can write down a general equation. This will be my equation of motion. The Eex minus kvdx will be simply m time a, which is a equation of motion here for the electron which is moving in the solid. Now you see, under the steady state motion, what will happen? The average velocity of the electron is constant, going to be constant. Why? Because you see, the because of this electric field, the velocity is increasing. See, the velocity is increasing here over the time, but because of this resistive force, the will actually is going to be balanced out. So because there are frequent collisions, so acceleration of the electron by the applied electric field is getting perfectly balanced by their frequent collision with the lattice ion. So in what will happen in that case, we can say that basically over the time your my drift velocity will be constant. So if I put that, this will be 0. So I can figure out basically my k, which is the constant here is simply m by tau here. Now, if I input that m by tau there in that equation again, so this will give me a general equation of motion of conduction electron. So this is my general equation of motion for the conduction electron in solid. Now so this is the general equation of motion. Ex is constant, we assume. Now suppose instead of a constant field, if we apply a step field means, so this is, you see this figure here, electric field and versus time graph. So I have a step function. So means my electric field is 0 below some time t equal to 0, and then it approaches to some constant value which is Ex0, and it remains constant up to the time when I turned off the electric field, T off. After that, again, electric field is 0. So I mean, it remains basically constant over the time between 0 and T off. So I can just write down basically, you see, so this is my equation of general equation of motion, and this is a first order differential equation, and the solution is this much. First order differential equation, I will assume that you have already solved this. This is very similar to the capacitor charging problem, RC circuit, probably you have done. So this is the first order differential equation, and this is the solution of this equation. This is the solution. This is the solution for this equation. Now what I will do actually here, you see, and when you apply basically these boundary conditions also, okay, you apply this boundary condition, you will get this solution. So what we learn from here, we learn that my drift velocity actually exponentially rises exponentially with time. It's like a capacitor charging. So as soon as you apply a step electric field, the drift velocity will exponentially rise, and it will saturate to some value here. This will saturate to value here. So you can see here for t, if I just put t tends to infinity here, if I put the t tends to infinity, this term will go to 0, and you will get basically, this will be this term, this part. So this is going to be, this part is going to be E tau Ex divided by me. Okay. So this is my, this is going to be the drift velocity at this point. Okay. And then after that, when you turn off, again, the drift velocity does not goes to 0 immediately, just takes some time, tau. So this tau is the basically your rise time. So you see what we learn here is a very interesting thing. This, see, one of the very important fact is that this tau which we are talking about, which we have determined, you remember we did one problem also, this tau is the mean free time, and which is of the order of 10 raised to power minus 14 seconds. This is very, very small. You see this time is very small, which is the time between two successive collision. So if I apply a step voltage, so what we learn, if you apply a step voltage instead of constant field, if I apply a step electric field, or we say step voltage to a conductor, the current, because the V will make, you see the V, because of this V I can just write down it is Ne, the current density will be simply NeV dx. So it means as you apply the electric field, step electric field or voltage, the current does not follow the voltage immediately. It means current will rise exponentially, and as it is in LR circuit. So you remember that, but you see here we don't have any inductance, we don't have any capacitance, but still this is the intrinsic delay in the current density. Okay, this fact you remember. So when we have a time dependence, so term here, so you get an intrinsic delay in the current density. Current will never rise basically to this value immediately, but it will follow some maybe this way, this exponential way. So this is because it will because you apply basically a step field. Now we'll see what will happen if I apply AC electric field. So what is AC electric field? I can just assume a simple form here that my AC electric field E is some constant which is amplitude time Ex naught exponential j omega t. So my electric field is varying with frequency omega here. Omega, you know, omega is angular frequency. I can write down omega is simply 2 pi time f, where f is the frequency in hertz. So this is, if I just, you see, if I use this E here instead of Ex, and I can write down the general equation of motion for the electrons. This is my general equation of motion. So now the solution, again, the solution of this will be simply, you see, this is a first order differential equation. You can just you can do this, you can solve it, and this will be basically a simple solution here we get. So see, the solution says that basically my drift velocity is a function of frequency also. So whereas you remember, before, the drift velocity was simply, if I write down the without, in the DC case, it was something E tau and Ex by m. So me, okay, so that was a drift velocity. But now it got basically, you see my it got some frequency dependence term here. Okay, now the drift velocity depends on frequency. Now the current density, you see the current density is simply Jx is nev dx. And also you remember current density is also J. I can write down J is sigma time E, where E is the electric field. J also got a relation with the conductivity uh, in this way, the electric field. J is conductivity time electric field. Now in this case, because I'm just applying the AC electric field, I will write the AC conductivity. So I can just, you see, I can use these two equations, because this is my V, V dx. I can input this here, E and V dx, and then you equate these two equations, this equation and this equation. I can just figure out basically the AC conductivity. So the AC conductivity comes out to be E square n tau divided by me 1 plus j omega tau. Now you see this term is the sigma naught, or sigma naught is nothing but the DC conductivity, like we have already discussed before. This is a DC conductivity. So you see my AC conductivity, my conductivity under the AC electric field depends on the frequency of the applied electric field in this fashion. Now you see, I can I can just write down, because now it got a complex number. It's J is complex number. So I can just write down the total conductivity as a portion of the real part and then the imaginary part here. So you see, I can just divide sigma prime and sigma double prime. Sigma prime is real, sigma double prime is basically your uh, the imaginary part. So sigma prime, if I just you see, if you multiply, like if I can just write down, multiply both by 1 minus j tau, 1 minus j tau, and then you do a little bit mathematics, you see you get basically this term. So this is my real part of the AC conductivity, and this is the imaginary part of the AC conductivity. Now, you see, if now we talk about the energy dissipation, which we call the Joule laws, when suppose we have a conductor in which current I is flowing and the resistance of the conductor is R, then we know the Joule heat loss is I square R. Actually, it depends on the real part of the real part of the conductivity. Okay. Now see, the omega tau is very important. What is omega? Omega is the frequency of the applied electric field, and tau is the material property. Tau is a mean free time, and this is something of the order of 10 raised to power minus 14 second. Okay, so this is very small mean free time. So if I use that, if now I use the condition that if my omega tau is less than 1 or less than 1, this omega tau is less than 1, then what I will see, my basically this you see, then my this real part is going to be equal to the DC conductivity, because this omega tau is less than 1, I can neglect that. So in that case, you see my sigma prime will be approximately equals to your sigma naught. So which is basically or the AC conductivity will be having a larger real part, which means there will be a finite Joule loss. So for low frequency, very low frequency, there will be a finite Joule loss. Now you consider the case when my omega tau is greater than 1. What does it mean actually? It means omega tau is greater than 1 means my omega, because tau is 10 raised to power minus 14, it means my frequency has to be greater than 10 raised to power 14. So see, this is very huge in terms of frequency, angular frequency. 10 raised to power 10 to power 14 is a very huge frequency, very high frequency. So in optical, maybe near to the optical region. So it's a very high frequency. You see, when I say this is this is larger, then you see, you can just get from here that your sigma prime will be almost like sigma naught omega square tau square. So which is, so see now basically your conductivity is real part of the AC conductivity will decrease as a function of frequency here. So as means like your it means that your joule loss will also decrease sharply with the frequency. So that is actually shown here. So basically this is the AC conductivity divided by the DC, and you see as we increase the frequency that actually decreases. So up to some frequency value it is almost constant, and for larger frequency like 10 to raise to power 14 per second kind of that angular frequency, this actually decreases sharply with the frequency. So means the material shows frequency dependent conductivity, which is known as AC conductivity. Now let us have some discussion here with this problem. Suppose we talk about, suppose the mean free time. So I'm talking about the copper, in which the mean free time, which is tau, and the means or the means is basically given, which is this value 2.5 10 to 1 minus 14, and the room temperature conductivity is also given. So this is my room temperature conductivity, which is rho naught, or the DC value. Now we need to figure out what is the change in, what is the ratio of AC conductivity to DC conductivity. Means if I just start to compare basically both for basically if I change the frequency from 100 for two different frequencies, 100 gigahertz or 100 terahertz actually. So if I put basically electric field which is varying with 100 gigahertz, this copper wire, and we would like to figure out how the its conductivity is going to vary actually. So see, in general, this is, we have already discussed basically how the AC conductivity depends on the frequency. So we know this formula. Now let us figure out for frequency 100 gigahertz. So frequency 100 gigahertz, we can determine basically omega. Omega is angular frequency, which has a unit of radian per second to 2 pi f. So you can determine here the omega tau. So this is omega and tau. So it comes out to be 0.0157. Now if I input here, we'll get basically this function 0.997 minus j. This is so you see here, if I see this is the real part, this is the real part. The real part is almost basically, so you see this is 0.997. It means if I just multiply by rho naught, which is DC part, this my AC conductivity is almost equal to DC conductivity, DC value. So means it is almost like frequency independent of for up to, for the metal which is 100 gigahertz frequency we are applying. Now let us see for the 100 terahertz. 100 terahertz means something like 10 raised to power 14 hertz. Okay, if I use that, so see, if I use that and same you put the omega tau in this time, we get 15.7. If I use that value, it comes out to be, see here this function, it comes out to be my AC conductivity is now becomes much smaller than the DC conductivity. So it means for actually for metals, it's basically if you go for very large frequencies, you remember we are not talking about the skin depth here. So this is purely the bulk material we are talking about. So if you go for very large frequencies, which is 100 terahertz, okay, which is 10 raised to power 14, then basically the material shows it's like conductivity decreases with the function of frequency. Now let us discuss basically the charge motion under electric and magnetic field. So so we have already learned that how the electron, we already wrote the equation for electron drift velocity in electric field, DC electric field, as well as in the AC electric field. So suppose now we would like to figure out what is the current density in the presence of electromagnetic field. Now we have both electric and magnetic field. Now suppose we assume a random electric field direction. So random electric field direction, I can write down this term. My E is simply has a component in x, y, and z direction. X, y, x cap, ex, y cap, ey, z cap, ez. Okay, so we have my electric field in general is in x, y, and z direction, but the magnetic field is actually in the z direction only. That's just for the simplicity only. Otherwise, it is too cumbersome to solve the problem. Now you see, when we have a charged particle under electromagnetic field, we know that there will be a Lorentz force. Lorentz force, and that Lorentz force is will be having a electric field. So that Lorentz force is given by QE plus QV cross B. So it's a general formula. Now what we'll do, I know just so suppose the charge particles are moving in the drift velocity Vd here. So I can write down F is ma, a is dvd by dt, QE and QVD cross, and B is only Vz jet cap. Okay, that we'll put here. Okay, so you just put this value, so I can just write down. So you just from here I can just simply you can just have some kind of integration here, the time dependent parts. You see the Vd, if I can get from here, the Vd is simply Q uh, uh, tau is basically on mean free time, m e plus Q tau Bz by m, and this is Vd by z cap. Now you see, now I'll use basically, now I'll use explicit form of E. Now I'll just input here E here. E I can write down x cap, ex, all the components, y cap and z cap. So if I just write down the component wise, so I can just also write down Vd, diff velocity component wise. So I have Vx will be simply this much, and you need to basically, you see the correspondingly I will get basically the Vd here. So this Vd is simply Vdx here, or Vx I just wrote here. So you get basically the diff velocity in x direction will be given by this function, this relation, diff velocity in y direction. I can also write down diff for z. You know that if it is in the z direction, z cross z is basically 0. So this will be no magnetic field component here. That's why. So if you write down, we'll get basically 3 equations which correlates basically the drift velocity. So it means if I have charged particles which are moving under electromagnetic field, so they will be having drift. They will be drifted in x, y, and z direction, all the 3 directions, and this is the relation how they are different. Now suppose you see, so the charged particles is suppose moving under the electromagnetic field, and this is z direction. Suppose it is moving in this direction, this is x, and this might be your y direction. So suppose electron, this is the electron which is moving. Now you see, under the since the magnetic field is suppose is basically perpendicular to the, if suppose perpendicular to the velocity of the electron, in that case there will be a force which will be acting on the electron. So see, we know, and because of the magnetic field, the force, magnetic force Fb, which is Q V cross B. Okay, so which it means the magnetic force is perpendicular to the both the velocity direction and the magnetic field direction. So because of that, you see, it will be it will cause some kind of centripetal force to the charged particle, and charged particle will rotate. Actually, it will try to make a circle here. So there will be a centripetal force which is mv square by r, and we can equate with the magnetic force here. And if you equate that, v by r is omega. So you see, I can just write down basically relation omega will be simply qbz by m. So this is known as cyclotron frequency. This is just the definition I'm showing. I'm just saying that. So I can also write down omega is under the magnetic field, charge particle is moving, q by m bz, which is well known. Now what we will do, actually, I'll just here just I'll just in these 3 relation 1, 2, and 3, I will just use this term omega instead of q by m into bz. That's it. So this is my 3 relation again I just wrote, and then now I can just write down basically. So you see, now solving for equation 1 here, this is my equation 1. I can input y from here. You can input the y value here, and then you write down here. This is the way you wrote. Vx will be simply q tau by m ex plus omega tau bz, and then vy value I can input from there. We have just determined from there. Now just little bit manipulation, you do that, and then you can figure out basically your Vx here as a function of Ex and Ey. So what we learn, actually, we get actually the Vx, which comes out to be q tau by m, which is a function of Ex and Ey, and divided by 1 plus omega squared tau, where omega is simply, you see, omega is simply your cube. Omega is, we have determined q by m time Bz, cyclotron frequency. So this is my Jx. So I can write down the current density, which is n time Q into Vx, which we have already learned before in Drude model. So I can use that. Then I can use this Vx value here. I can input the Vx value here, and you can get basically the current density. So if charge particles are moving under the electromagnetic field, then basically if I have a solid in which charge particles are moving under the electromagnetic field, the current density will be simply uh, uh, sigma time, where I can just rearrange, because sigma I have defined nq square tau by m. So the simplest form you can get is conductivity Ex plus omega tau Ey divided by 1 plus omega square tau square. Simply I can also find out basically the value of Jy, which is from this function Vy. So Jy will be simply Jy will be nq Vy. Then you have to input the value of Vy from here. Okay, so you get basically three relations. So what we learn? So in presence of magnetic field, the current density is generally not parallel to the electric field. So you see, if I have only electric field, then current density J is sigma time E, which means current density is basically parallel to the electric field. But when you have the magnetic field, the current density is not actually parallel, but it got basically, you see, it is basically having Ex and Ey, both component. Here you see Jy is having Ey and Ex, both component. And so means it is not parallel to the electric field. So but you just keep in mind, see, this term is very, very important, omega tau. So the value of omega tau, so this omega tau value, so the omega tau value, if it is less than 1, then you see in this case Jx will get basically simply proportional to Ex. So if omega tau is less than 1, or if I say tau is omega is less than 10 raised to power 14 second inverse, because your tau is you see mean free time is 10 raised to power minus 14. So means for these frequencies, maybe you can still assume that this effect, application of magnetic field, has no effect actually. You can see in metal. So if you apply the magnet in the metal, large magnetic field, basically this anisotropy, which is called basically you got the Jx is also function of Ey, which is not there. So this anisotropy is very, very small if basically the frequencies are very, very small. But for large frequencies, if my omega tau is greater than 1, you can still see the anisotropy in the Jx, or you see basically that current density is not in general parallel to the applied electric field. The other thing which is very relevant actually here, you see the number of electrons also. So you see the conduction electrons are largely insensitive to directional change, because there is a dominant scattering mechanism. So if I talk about the metal, you apply the magnetic field in there, basically this kind of deflection of the electron because of the magnetic field is not that much sensitive, because there are so many scattering mechanisms, so many scattering centers are there, and so many charges are there. So when you average, this magnetic field has almost no effect. But this anisotropy is more relevant in semiconductor, where we have the rare distribution, means the charge density is very, very low and you have a small number of scattering centers. And in that case, basically you can see that the current density is having anisotropy, like you get basically Jx, which is function of Ex and Ey, both actually. So so when we now we understand basically the charge motion under the electromagnetic field. So what we can talk about now, we talk about the Hall effect. What is Hall effect? So you see, in Hall effect we have a very thin slab here. We have a very thin slab, okay, and we apply, this is positive, this is negative. So we apply basically we apply a voltage here between the two, along the length of the slab, which is in the x direction. This is x direction. And then we apply basically this magnetic field, which is basically in the z direction, which is perpendicular to the slab. Then what will happen actually? So you see, this is the current direction, charges are moving from positive to negative, and because of that there will be a Lorentz force which is acting on the this charge particle or electrons or holes, whatever. If it's semi-electric is hole, then what will happen basically, because charges are moving and there will be a two field. Number one, this field which we apply V. So because of that, this is V we are applying, and there's a certain thickness of the length of this slab. So I can think of there will be some electric field which is there. Because of that, this is electric field is E, the some force, electric force, and because of magnetic field there will be magnetic force. So this is the total force. So this total force is applied there. Because of that, the charges will get deflected. So so charges are moving, so they get actually deflected out. So electrons will move in this direction. Okay, they will get deflected out. So electrons are starting moving to the width side. So this is my width along the y direction. So this is the y direction. The electrons will move from this side to this side. Okay, so to this side they will come. So when the electrons are moving to this side, you see, when the electrons are moving to the opposite side, the width wise, then this charge separation, because of that, the charge separation, there will be because of that there will be a voltage which will generate here. See, oops. Mhm. I think there is the slide. Wait a second. I'm just trying to reload again. Wait a second. Yeah. Yeah, I'm just sharing again. Wait a second. I'm just sharing again. Yeah. So let me see. You can. I think you can see the slide. It is okay. You can see the slide, no?
Yes, sir.
Okay. Okay. So yeah.
Visible.
So basically, now you see, because of that, you see the charges move from the widthwise. So we get basically charges are going to be built up here, and when the charges are building up, then it will be so it means there is some current which is moving in this direction. I can say there is a current density in the y direction. Okay. Before that, the current was already moving. We had the current density in x direction. And because of charge, because of magnetic field, it get deflected out jy. Now, so this current will be so they'll because of that current, actually charges are going to be built up there, and so this charge separation will continue. How long it will continue? This will continue till there is a voltage which is generated, which is known as Hall voltage. So there will be a Hall voltage which will generate. Electrons are suppose moving from this side to this side, so there will be a positive charge there. So the electron will get a attractive force because of this positive charge, and that generates some kind of voltage between that. So you get basically, which is shown here, which is already shown here. This is the Hall voltage. So so when basically this so this Hall voltage will generate, and this will counter the, because of that Hall voltage there will be force on the electron which are moving, and that I can say is going to be force, electric force will be simply E time V QV. So E time VH. Okay, that is the force. So it's a magnitude of the force, electric force. So so that will be generated there, and yeah, QE. So the VD, and then there will be I think this V by D. So we, and then this width also width. Yeah. So in, so what will happen in the equilibrium state? When the equilibrium will come, then this Jy will go to zero, because there will be a force because of Hall voltage we generated. That is the Hall voltage. Because of that, electric force will be there, and this force due to the magnetic force. Because of that, actually, it was deflecting. So at equilibrium condition, the drift velocity along y-axis will be zero. Now you see, we have already calculated. Basically, this is the what is the current density in y direction and then electromagnetic field in general. So what we can see there, so I already wrote that these three equations there. So what we can do, that we can just make this Jy 0, okay, under the equilibrium condition. And this, since there is no drift velocity along y-axis, so in that case, my Ey, what will be my Ey will be simply Hall voltage, Eh. Okay, so I can put the Ey is Eh, and then you simply make it zero, then you will get basically Eh Hall voltage. I can figure out how much Hall voltage, omega tau Ex. Now Ex, I can just write down, still I can assume the deflection is less, so I can still write down basically that Jx is sigma time Ex. I can write down here. Okay, so you just a little bit rearrange omega. You see, we have defined omega is q by m time Bz, and if you just put all these values here, you see I can write down Eh is 1 over Qn Jx Bz. So J, now these are the known quantities. Jx is the current density in the x direction. You see, this is the current density in x direction, which is basically, which we know basically, because this is the voltage you are applying, and this is the current density. And Bz is basically the applied magnetic field. So it comes out to be 1 over Q time n. So 1 over Qn is known as the Hall coefficient. Okay. Now this number is very, very important, 1 over Qn, because why? Because if suppose the Hall coefficient is positive or negative, it will tell us basically if Q is, if it is negative, it is means it is electron, the carriers are electron. If it is positive, the carriers are hole. So we just get the idea whether this is electron or the hole there, the type of the charge carrier. Also we can determine basically n, which is basically the carrier density also. So Hall coefficient, Hall effect is by more than 100 years, and then it's still very useful determining. Still all the labs are having this experiment where we can easily figure out the type of the charge carrier and the carrier current density. Now you see the mobility, we have defined the mobility here. So mobility is q tau by m, we have already learned. So you can just also write down in this way, because sigma is nq squared tau by m. If I just combine these two terms here, I can write down mobility also in terms of basically Hall coefficient, which is conductivity times the Hall coefficient. So means like there are so that is something basically. Now till now we have discussed basically only one type of charge carrier. Now in semiconductors, generally we have two types of charge carriers. So like I can have, suppose I have one charge carrier which is electron q1 of density n1 and hole q2 of density n2. Then you see I can write down basically the current density as the total current density will be sum of the j1 plus j2. And I can just also write down this way, j is q and q and v. So I can write down that. And the conductivity will also be sum of the conductivity of these two channels. So they will act like two separate channels, electron and holes, and I can write down that actually. So see, at room temperature in semiconductor, the relaxation time for the semiconductor is is small, or I can just say that omega tau squared time is small. Here omega squared tau squared term is small. I can just use that. Then basically I can just write down the Jx or the Jy. Again, I can rewrite these equations in basically in this form. So this is the two equations, the same equation, this equation for Jx and Jy. Only thing is I have just used sigma as a summation. The total conductivity is summation of the two channels, sigma 1 and sigma 2. Same one, the current density is J1 and J2. So Jx will be simply sigma 1 plus sigma 2 here. Sigma is sigma 1 plus sigma 2. So I just get this two equations of the charge carriers under electromagnetic field, where the field is in this case is in the z direction only. Now, so I just use basically the same condition that under the equilibrium condition, there will be Hall voltage will develop and there will be no drift velocity along the y direction. Means Jy is 0. So if Jy is 0, if I put that value, you see I can rearrange. So you get basically my Hall voltage in case of the when we have two types of charge carrier, which is given by simply this function. And sigma is any mu. I can just again write down this in terms of carrier concentrations also. So see now I just more generalized more form, which is more shown in the books actually, like mu n v p for hole and n for electron. So this is the general Hall coefficient when you have two types of charge carrier. So what is important is actually, you see this is the table which shows you for different metals the Hall coefficient. And if I have semiconductors also, I have not included, but for semiconductor also you can see the Hall coefficient. You can easily depends on the carrier concentration and the mobility also. But what we learn here, you see, we learn that in semiconductor the sign of RH strongly depend on the dopant density. Means which is, you see, P and N are the dopant concentration. Carrier concentration is same, I can assume similar to the dopant concentration. So if you see, if my material is having the same dopant concentration and they have the same mobility, my electron and hole mobility is same and they have the same concentration, I can the RH can be 0, the Hall coefficient can even be 0. The Hall coefficient in case of like it can be positive or negative depending on basically the function of mobility as well as the carrier density also. So depending on these two numbers, this is important, this factor is important. So depending on whether this is going to be greater than 0 or less than 0, you will get basically positive or negative Hall coefficient. Now, one thing is very interesting. You see, there are some metals like beryllium, there is other metal like tungsten or cadmium, for which basically we obtain Hall coefficient positive. You see, most of the time you say you get basically the Hall coefficient is negative, and that is also fine, because negative means the majority, basically the carrier are electron. But in this case of beryllium or cadmium, there are some metals for which we got the positive Hall coefficient, and that is because of their basically the way that their Fermi surface is very different. That depends on the Fermi surface, and their basically the band structure is such that the carriers are actually considered to be whole. There still they are kind of metal. So this is a general maybe thing here. If I have basically kind of a silver one ribbon, metal ribbons, you have a silver ribbon here, and which is having a width of 1 centimeter and thickness. This is a thickness T of 0.2, and suppose perpendicular to that we apply a magnetic field which is 1.5 Tesla, and along the thickness and the n number electron density is given, we need to figure out the Hall coefficient, Hall voltage here. What is the Hall potential here? Hall voltage or Hall potential. So Hall potential is given by this function we have already determined. VH will be simply Hall this electric field EH divided by width, because it is like applied along this VH is applied along that actually only. So you can see I can just write down Gx is I divided by area. Current is already given 100 ampere. You can just put the values only. Okay, then you can figure out. So the Hall, you see, the thing is the Hall coefficient, Hall voltage is coming out to be microvolt. So you see in case of metals, is the value of Hall voltage is very, very small. It's very small. So that's why I just would like to say that actually for most of the time, like the for metals, these values are very, very small actually. So it is more relevant to the semiconductor where you have this density. This density is much smaller. So you can just see the deflection. Charges are really getting deflected there. One can see that. Now, so because of time, actually, I'll just maybe uh, skip that part, or maybe let me continue. Then another part I can continue tomorrow also that magnetoresistance part. So basically, we have learned about whatever we have learned was the normal like Hall effect, just for where we determine this is the geometry. We determine the the Hall coefficient, and we know because of the charge carriers are deflecting because of the magnetic field, we get the Hall voltage generated across the way. Now you see, now you suppose we have the same slab, we have a same slab, suppose, and you lower down the temperature. If I lower down the temperature, and this slab thickness is very, very small, so that we have a two-dimensional system. Two-dimensional system means my electrons are now confined. They cannot move along the z direction. So they cannot move along the z direction. Suppose this thickness is of the order of a few angstrom only. So or Fermi wavelength, it is less than the Fermi wavelength. So I say that my system is two-dimensional system. Then what was, and you we do this measurement as suppose some millikelvin temperature, okay, and you apply a very high magnetic field. What was actually observed? uh, See here, you see, if I just this is my Hall coefficient, same thing. So my I got, because in Hall effect you see we get two types of resistivity, because uh, uh, because of the Ex and because of Ey because of the Hall voltage. There is a field because of the Hall voltage. So we get two resistivity, one resistivity term which is because of the Hall voltage, which is rho xy, and one along the length of the structure, like you can see here, like here. So this is Ex in this direction and Ey in this direction. Okay, so you see, so we have two resistivity terms here. Now if I just talk about basically how these two resistivity depends on the magnetic field here. So you see, you can just little bit rearrange that. I can rearrange. So you see, in this case, in the x direction, the resistivity is like independent. It does not depend on basically the magnetic field. But in the Ey term, I can just see this is the Ey term. I can write down Ey is simply is a function of applied magnetic field. So resistivity will be proportional to the applied magnetic field. It will be it should proportional. So you see, this is in general. So resistivity is proportional to in xy direction. It should in xs direction it is constant. It is independent of magnetic field. Whereas actually in the in the y direction it should be proportional to the magnetic field, which is which we can learn from the normal Hall effect. But for this system, when you lower down the temperature and you use with the two-dimensional system, what was observed? It was observed, you see, this red one is the resistivity in xy direction, and green one is basically the resistivity in the x direction. You see, we observe very real. You see, it's a very interesting one. We observe that resistivity is even goes to zero, actually almost zero. It's we get the resistivity only for certain values of magnetic field, and basically also we obtain in xy direction it shows some kind of plateau behavior. So so this behavior changes completely. So just for the introduction, but I don't think like we have sufficient time to discuss this. So I will stop here, and maybe tomorrow, that whatever is left, a small magnetoresistance part, I will just take that. Okay, thank you.
Yeah, thank you. Thank you very much, sir, for a very, very wonderful talk. And now session is open for a question from participant. So participants, if you have any question, you may please write in the chat window. And one question is already being written by one participant. It is about the Hall effect. One participant is looking to just understand again what is please is asking, please explain Hall effect again.
Okay. So let me just go through that. Yeah. So you see what happens actually. So this is my suppose this is my material here. Suppose if even you take basically the electrons metal, this is a metal slab, and you apply the voltage along this x direction. Okay, so you apply the voltage along the x direction. Let me make it like the full screen. In the x direction, so there will be a field because of the application of voltage in x direction. There will be a field. I can write down this field E. There will be a field because of the component will be in the x direction. Oops, sorry. Yeah, this field will be having a component in the x direction because of this voltage. Now, so we have only applied the field in the x direction, and because of this there will be a current in the x direction, and that current density I can write down is n time E basically mu x, or I can write down it is sigma time Ex. Okay, so this is the current density in the x direction. Now, this is when you don't apply any magnetic field. But when you apply the magnetic field, we learn that the charge particle, because of the magnetic field, there will be a Lorentz force which is acting on the charge particle. There is additional force QV cross B. So because of that, this force will be, you see, this is the magnetic force which will be, so if charge particle is suppose moving, having a velocity in this direction, so in v direction, suppose charge particle is there and you get the magnetic field in this direction, then you get basically, you see, v cross b, you apply the right hand rule, so v cross b will be a force in the y direction. So this will be your force because of, and because of that force, electron will be basically moving towards the width side. So they are moving, but they get some kind of drift. So they move, but they start drifting there. So charge particle will start drifting this side. So because of that, there will be a formation of current in the y direction because of this force. There will be a formation of current in the y direction, and this current will be simply Jy, which will be simply, I say, now I can write down is a function of rho xy, maybe Ey. Okay, and what will happen because of that, when the charges are moving, there will be a potential which will be starting, because charge, now you get a charge separation. Whenever you have a charge separation, there will be a potential like voltage difference will form. So this potential difference is, here you see, is Vh, which is Hall voltage. So this slowly build up, charges are moving, so slowly you see the V is simply Q. V depends on the proportional to the charge. So as the charges are building up, your Hall voltage will increase. There will be a time, because now this current Jy depends on this Hall voltage, because Ey is nothing but, I can just in very vague way I can write down Vh, some V small h divided by the width. Okay, so this is building up. So this is, so when the, just basically this current, because of Vh, and the direction will be different, opposite, because of this actually the charges are getting, now positive charges are there, so electrons are basically attracted to this left side. So there will be a time at Jy will go to 0, when the electric force because of this Hall voltage will, so you get because of that you get basically, we have just figure out, so we put this condition and we get, because of that we get the Hall voltage and then Hall coefficient. So this is the Hall effect, because in the Hall effect we could able to determine the carrier concentration and the type of the charge carrier.
Yes, thank you, Prasad. Another question is about the book. One participant is asking what books are you would be referring for this?
Yeah, so I am referring the Kasab book, KASAP, Kasab.
Yeah, Kasab is very good book. There is one more question. One participant is asking how we know that electron sees core. How do we know that electron sees the core by scattering from first session? The question is from first session, and how do we know the electron sees the core by scattering?
How? Okay, so the question is like how the electron sees the scattering.
I think so. Yeah, question is not very clear. I think so. Yes.
Yeah, so see, there are different ways experimentally also one can figure out that also, because so this first of all, that was the model. Like we whatever we have discussed was just the model only. So like the model was based on the assumption that there is only thing electron actually get deflected not because of charge, but they are getting deflected at the scattering centers only, at the positive ion core. So that is assumption, but it is quite valid assumption. And so there are certain experiment like based on that people can determine also scattering, this mean free time also it is determined. Actually it is, we are able to determine that values also by applying, basically there are some electromagnetic wave rays you can like apply, basically you can put the metal under the electromagnetic field and you can do the experiment how uh, the charges are getting scattered with that. So there are certain experiment people can do that. So these are the experimentally observable values, like, but like visualizing is like this is just the model, like you can, no one can actually visualize like how it is getting scattered. So but actually they are scattered because of they are the charge, different charges are there. Actually the reality, this is a potential field, the new at the positive ion core there is a potential field which is because of that the charge carriers are deflecting there.
Yes, sir. Thank you, sir. Uh, One more question is there. Why Hall effect is significant in semiconductor than the metals?
Yeah, that's a good question. So you remember like I have discussed that in when you determine uh, the, let me just go back to that slide. Yeah, so you can see here. So see here, in case of basically, you see, here we get the Jx, which has the both component Ex and Ey. Since it got the Ey component, that's why we are getting basically deflection in the y direction. So see, if I talk about the metals, so in metals normally this tau, in case of metal the tau is around like 10 raised to power minus 14 second. So mean free time is 10 raised to power minus 14 second. Whereas in semiconductor, if I talk about the semiconductor, in semiconductor, this is something like 10 raised to power minus 12 second. Okay, so this is one difference here. So when you are talking about like omega tau, see in this case my omega tau should be greater than 1. That is one condition here, because if it is less than 1, then this term is going to be insignificant. So you see it means my tau should be larger. uh, yeah, so that is one condition we get here. In semiconductor it is around peak like picosecond, whereas it is actually minus 14 second. Other thing is basically the frequency you talk about the, so other thing is basically the other thing is sigma here. So sigma has this n number here. N, what is n here? So see this n is basically the carrier density. So in case of metal, the carriers are very huge number of carriers are there. So there are so many scattering events are there. So even the deflection is there, but on the average, you say there is not much deflected. So you can think of like some, like if someone is moving in a very crowded area, and then you see you don't get much deflection, but if you are having in the maybe in the rare maybe a place where the scattering centers are far, they are far apart, then you can see the deflection very easily. So there are multiple effects there.
6:30 वो है.
Yeah.
Yes, thank you, sir. Participants, do you have any further question? Okay, so it seems there is no further question, though all the participants is asking few question about the attendance and all. But there is one question Ankita Dikshit has written, sir. The question says, why quantum Hall effects does not occur in one day? The question is why quantum Hall effect does not occur in one day.
Yeah, so see, the point is basically the in the case of like the two-dimensional materials which you talk about. So in two-dimensional materials, the charges you see, because quantum effect, when we talk about it, is I have not discussed actually the theory, but that is because of the Landau levels which are forming there, and the edge states are playing major role there. In 1D system, you don't have the edge state. Actually, how the current is flowing there. So if I talk about, if suppose if I have a maybe let me just maybe tell you. So if you have a two-dimensional system, suppose you have two-dimensional system, and if you apply very high magnetic field at very low temperature, what happens? The charges, electrons are actually getting deflected, and they are deflected in such a way that they make a complete circle actually, if you apply very high magnetic field. So the so that is one thing. But actually, so they make a complete circle. Now these circles, which circle they make is quantized, because you know that charges, when they make a circle, like in Bohr's atom problem, you see they make a circle, but all circles are not possible. That's why the density of states get actually discretized there. There's a Landau labels which we know as Landau level. But actually, and so there is no current which are flowing because of this circle, because electron will make a circle, they will move around, but they don't make any time, they won't flow, but there is a current. So how the current flows actually in case of two-dimensional system, in the when you apply the magnetic field under very low temperature, then basically in quantum Hall effect, the current flows because of the edge effect, because at the edges the circle cannot make full form, because they can deflect, but they cannot make, because other side is air actually. So the actually current flows from basically from the edges only. So those are the there. But if you have one dimensional system, so see, you have already made the restriction. Now the charges cannot move in this direction also, in this direction also, they can only move in one direction. So you have only one direction where you apply. That is the region actually. That's why people are you don't have the edge states there. That's the region there. But actually, I just kept this thing little on the lower side, so that we should not discuss in detail that. We don't have much time to discuss that.
Yes, yes. Thank you. Thank you very much. It seems there is no further question. So I express my gratitude to Professor JP Singh from IIT Delhi to deliver lectures for this program. And so you may please share the PDF files of your lecture so that we can share it with the participants. So
Okay,
those
sure.
participants who could not attend the lectures or miss some portion of this due to the internet connectivity at their side, they can again go through all those lectures. And after today, means tomorrow also, we have lectures by Professor JP Singh ji. And after that, sir, you may please share 10 multi-choice questions, MCQs to us for the quiz or exam, which we will be conducting in between, let's say, in between of 6th or 7th day. And
Yeah, sure, I will do that.
yeah, yes. In that way, like every speaker is providing few questions, and then we will combine all those questions, and we will prepare a quiz or one exam paper. I can again see the chat window. People are writing, "Thank you, sir. It was a very nice talk, informative talk." Many many participants are appreciating a lot. Participants, you are asking about the Canva. Canva is having some issues. So till the issue is resolved, we would be sending all the lectures, PPTs, or other notes to you through Google Drive link. You will be getting all the information on your email. All those who are not able to log in on Canva, please wait for some time. There is some issue with the Canva. So with this, now we have come to the end of this session, and then we will be again